By definition, if we're given a particular level of confidence C, we're going to say that the margin of error, also sometimes called the maximum error estimate or the error tolerance, this is going to be the greatest possible distance between the point estimate, the one you can compute, and the value of the parameter it's estimating, in our case, mu, the population mean. In particular, if we are looking at a population mean, this is very specific here, where sigma is known, again, that's the point of section 6.1, is sigma is known, then the margin of error can be computed in exactly this way. Specifically, it is the critical value, z sub c, which we computed at the top of the page, multiplied by the standard error. This is that standard deviation of the sample mean, which in particular, the formula for that is the standard deviation of the population divided by the square root of the sample. This is possible, and this is acquired only if two conditions are met. The sample has to be random, and part two is essentially trying to argue that the central limit theorem holds. That is, either the population is normally distributed or the sample size is greater than or equal to 30. So if you recall how much I tried to make sure everyone was aware and writing down, making sure that the central limit theorem held in the last chapter and going through all those details, we're going to have to continue to be that careful as we proceed because the central limit theorem isn't going anywhere anytime soon. So this is how we compute margin of error. One of the more difficult and sneaky parts of computing the margin of error is exactly the fact that the margin of error requires you to know z sub c. And as we saw above, computing z sub c can be a little time consuming and it involves utilizing the table. So please keep that in mind. Take a look at the next example as we revisit the data from the first example, and now, given a confidence level, we want to find a margin of error. Specifically, what we want to do is build a margin of error that will eventually be built into a confidence interval for a confidence level that is 95% confident. So, in order to even begin, we want to verify for ourselves and for the reader that this notion of margin of error is valid. What that means, we have to check that these two conditions are met. And you're going to have to do that almost every time. So we're going to verify here that so since sigma is known, that means that we're in section 6.1. That's the content that we're in right now. We know from a previous, when this example was introduced in example 2, I highlighted the fact that the sample is random. So the sample is random. That checks off the first part of that definition. And what's more is that the sample size was 40, which is greater than or equal to 30, which now checks off the second part of that definition. We now have enough information at our disposal to turn around and say that we can use the formula E is equal to z sub c times sigma over the square root of n. If you do not check this every time, you cannot use this formula. And so it's definitely going to be something that I'm going to be looking out for. The second step of the problem is finding z sub c. To find z sub c, it's exactly the same process we saw a little bit earlier. In this case, since c is equal to 0.95, because that's our confidence level, you could draw a picture, by the way, if it continues to help make sense. So we'll draw our sample distribution. Here's z equals 0. To the left, we have negative z sub c. To the right, we have positive z sub c, and in particular, we want this shaded region in between. We want this to have an area of 0.95. So the process is just like we saw before. Since c is 0.95, 1 minus c is now 0.05. This is the area of both tails, where then if I do 1/2 1 minus c, this will give me 0.025. That will give me the area of one tail. So negative z sub c is the z-score corresponding to an area of 0.025. At this point, we go back to the table, which we're going to do right now, and we need to find an area of 0.025. And we see we're almost there. If we start looking, we want 0.025. There it is, right there. So we'll use a slightly different color, maybe green. 0.025 is right there. And so that's going to correspond to negative 1.96. We'll import that result into the work above, and we'll end up with the fact that negative z sub c is apparently equal to negative 1.96, which tells us that if we divide by or multiply by negative 1, that positive z sub c is regular 1.96. And so at this point, if we want to find the margin of error, we see that E by the formula is equal to z sub c times sigma over the square root of n. And so now it's 1.96 times sigma, which was 7.9, over square root of the sample size, which was 40. And this is going to be approximately, if we compute this, 2.4. So the interpretation, if we had to sort of write this in words, is the following. We are, since the confidence level was 95%, we are 95% confident that the margin of error for the population mean is about 2.4 hours. So if we pick a sample of 40, any 40 employees, and we turn around and try to figure out what the point estimate is for that, and we allow ourselves a margin of error from that point estimate of 2.4 hours, what we've determined is that we're 95% confident that our given interval will contain the population mean. So the last step of this entire process is actually building out the confidence intervals. And building out the confidence intervals simply amounts to starting with the sample mean, x bar. We simply build out an interval where the rightmost endpoint is x bar plus e, where e is that margin of error, and the leftmost endpoint is x bar minus e. This is going to be referred to as a C confidence interval for the population mean. In particular, the way this is interpreted is that this means that the probability that the confidence interval that we build contains this fixed number, the population mean mu, is going to be C. So if we again keep using our same example and we import that data from example 4 and then the margin of error we got, import the data from example 2 and the margin of error we got from example 4, we can construct a 95% confidence interval for the mean number of hours worked by the grocery store employees. So what we saw before is that we know X bar is equal to 29.6, and we know that E was taken to be approximately 2.4. So the confidence interval is going to be, well, let's draw a real number line. We're going to put at the center of it X bar, which is going to be 29.6. And then to the right of that, we're going to build a magic point, and that point is going to be, by definition, X bar plus E. And to the left of that, we're going to build another point, which is going to be X bar minus E. But when we know X bar and E, we can actually compute these values. The rightmost one is now going to be 32.0, and the leftmost one is going to be 27.2. So what that means is that by taking a sample size of 40, we are going to be 95% confident that the population mean mu is going to live somewhere between 32.0 and 27.2. It does not mean it has to live there. It might live somewhere else, but we're 95% confident that it will live there. And so, if you want to write it in set interval notation, the interval is 27.2 to 32.0 with parentheses. What we've done today so far has been a lot, and it's been a lot of a sort of a step-by-step process as we figure out how to do this information. Now, if we put it all together, we can build sort of a step-by-step process here. If you're tasked with constructing a confidence interval for a population mean, where again, we're in section 6.1 here, so the standard deviation is considered known, then this is the step-by-step process. You verify that sigma is known, that the sample is random, and that either the population is normally distributed or n is greater than or equal to 0. This is essentially checking that the hypotheses of the central limit theorem holds. You find the sample stats, the size of the sample, and then the sample statistic, X bar. You find the critical value, Z sub C, that corresponds to your given level of confidence. This will require the standard normal table, as we've seen. Then we compute the margin of error, and then finally build out the confidence interval in question. This is the step-by-step process that we have to know and love and understand really, really well. On the next page, we have another example of going through this process. So here we have college admissions, and a college admissions director wishes to estimate the mean age of all students currently enrolled. But of course, predictably, finding out the mean age of all students might be taxing. So instead, he chooses to take a random sample of 20 students. And what he finds is that the mean age of the sample is 22.9. So the minute I read this information, I'm getting the impression that this is my n value, that the mean age of the sample, that's going to be my X bar value. We know the standard deviation is taken to be 1.5 years, so that's my sigma value. And we're told that the population is normally distributed. So this is all really, really good information that allows us to proceed. Proceed with what, though? Well, our objective is to construct a 90% confidence interval for the population mean age. The step-by-step process we detailed above has us begin right here by verifying all the given information. So we're going to do that first. What we're going to have to write down here is something along the following lines. Because sigma is known, the given sample is random, It's taken right there. And the population is normally distributed. All the hypotheses from step 1 of the checklist hold. And the conclusion is that we know then that the margin of error E can be taken to be z sub c times sigma over square root of n. Now we move on to step 2. Step 2 was item collection. We had to find the sample stats n and then x bar, and then step 3 says find z sub c. So with the given information we have, we know that n is equal to 20, x bar was taken to be 22.9, sigma, the standard deviation of the population, was 1.5. So with this information, we now find z sub c when the c is given to be 90%. Of interest, however, is that z sub c is only actually dependent on the c. So if you actually take a look at a previous example we did back on page 3, this entire introduction here was exactly, given a c value of 90%, finding those z sub c's. So this is the process we would ordinarily have to do in this problem if we hadn't already done it once before. So we're going to import this information in the question we're solving. And so we'll find that on page 3, we found that in this case, z sub c was 1.645. So the formula is, for the margin of error, E equals z sub c times sigma over the square root of n. This is going to be 1.645 times sigma, which was 1.5, over square root of n, in this case square root of 20. And if you go through that computation, we'll get approximately 0.6. So now that we have the margin of error, we need to build out the confidence interval. Remember that based on our process here, the confidence interval is taken down here, where the left endpoint is x bar minus e, and the rightmost endpoint is x bar plus e. So what we're going to end up writing here is those computations. X bar minus e, if x bar is 22.9 and e is 0.6, this is going to be 22.3, and x bar plus e can be computed to be 23.5. So what that means is that the population mean mu, with a 90% confidence, is going to live somewhere between 22.3 and 23.5. And if you wanted to build a picture representation of that, we would put 22.9, that's the x bar value in the middle, and to the left endpoint we would have 22.3, the right endpoint would have 23.5, and this in between would be exactly the interval that we've built. This is all sort of mathematical, so what is the interpretation that we want to try to adopt here so we can actually use these words to convey what we're trying to say? So what we might say is that this means that, comma, with 90% confidence, the mean age of all students is between 22.3 and 23.5 years. It's really important to note that we're using the word confidence here, not necessarily probability. If you do want to use the probability word, you have to be very careful. This exposition following this problem sort of highlights why you have to be careful. What we've determined here was that the 90% confidence interval was 22.3 to 23.5. But again, as we've been noting throughout this conversation, mu, the population mean, that's a fixed value. It doesn't change. So where some people might be inclined to say something like, there is a 90% probability that the actual mean will be in this interval. Unfortunately, this is the worst possible thing to say, because this phrasing somehow implies that the probability or the actual mean is this fluid variable that can live in different places, and you're now 90% confident, oh yeah, I'm 90% confident that it happens to live in there. What you're actually trying to say is this statement with the word confidence. That's the correct statement. That as your population, as your sample moves around, and for every sample, you build out an interval, what you're saying is that 90% of the intervals you build for each sample, 90% of those intervals will contain the population mean. It's a very, very subtle point, but a very important point when it comes to trying to actually tell people what you're trying to say. So please keep this in mind if you ever get asked to interpret or explain what it is you're doing. Now there's one last thing we have to talk about in section 6.1, because there's a glaring flaw in everything that we've done so far. The unfortunate consequence of confidence intervals is the following. As the level of confidence increases, which predictably is what you want to be ever more confident. Being 95% confident is better than being 90% confident. The problem, though, is that as your level of confidence increases, the interval that you build widens, which is not good, because what that means is that the precision of your estimate, the error that you're allowing, starts to blow up. And this is somewhat problematic. There is a way to fix that. The appropriate fix, the way to improve precision without decreasing confidence, there's really only one way to do that. Increase your sample size. The larger your sample size, the more precise your estimate. So the question you might have if you worked for a company is your company says, we want you to have, say, a 95% confidence, but we want the margin of error to be no more than like a really small percentage. So your only choice is to increase your sample size, and so the company might say, how many people do you need to sample? How many people do you need to call or poll or what have you in order to achieve the confidence within the error that we want? Well, fortunately, there is a way to figure that out. This right here is the error formula we encountered above. So in this situation, if you know the error that you're willing to work with, or you're desiring, you know the confidence that you want, and you know the population's standard deviation, it's a simple matter of algebra to take this given equation and solve for n. Doing so, what we'll do is we will rewrite this and divide both sides by z sub c. So we will get, on the left-hand side, we will get e divided by z sub c. On the right will be sigma over the square root of n. Then we can cross multiply, and we'll get square root of n times e is equal to z sub c sigma. Then I'll divide by e, and I'll get the square root of n is equal to z sub c times sigma all over e, where finally I'll square both sides and get n is equal to z sub c times sigma over e all squared. And so, If you know the confidence, the error that you want, and the standard deviation, this is the formula that tells you how big your sample size needs to be. If we wanted to write this down formally, we'll write out the following. If you're given a C confidence level and a margin of error E, the minimum sample size N needed to estimate the population mean is exactly that formula we had before. Notice that this is a minimum. Your sample size can be bigger, but this is the minimum that you need to achieve. This entire section, section 6.1, is predicated on knowing your standard deviation. What we'll talk about next section, and as it relates to this, is that if you don't know the standard deviation, there is a way to proceed. You can use little s. Recall that this is the sample standard deviation, and this will serve as sort of a substitute, provided, of course, that your sample is at least 30. That's what the assumptions we've been operating under. So the last thing we'll do in this lesson is take a look at an example of utilizing this formula. And so what we'll look back at we will look back at that example we've been seeing over and over again. And we'll say that this economics researcher wants to estimate the mean number of hours worked, again, by all grocery store employees in the county. And so last time this researcher only polled 40 employees. The question now is that if they wanted to be 95% confident in their estimation, and they also wanted to make sure that their error was within 1.5 hours, the question is, how many people will they have to survey? Well, what we're going to do is we're going to write down the information given to us. 95% confidence, that means C is equal to 0.95. We've already in this lesson so far talked about the corresponding critical value. The critical value for a 95% confidence level is Z sub C equals 1.96. If this was, say, an exam or something, you'd have to re-find this using the standard normal table and the process we developed earlier. But for now, we've already done it in this lesson, so we'll import it. We'll note here that the standard deviation, although not written out exactly in example 7 here, in a previous example when we talked about this problem, we observed that the standard deviation was equal to 7.9 hours. And what is new here is that this information is telling me that E needs to be 1.5. So the formula for the sample size we need is N is equal to the critical value Z sub C times sigma all over E, then squared. And so in this case, it's 1.96 times sigma 7.9 over E 1.5 all squared, which if we were to compute this would be approximately 106.56. But of course these are people, 0.56th of a person, not really relevant, so we're going to opt to round up. So what we'll say is that rounding up, the researcher needs at least 107 grocery store employees in the sample. What that tells us is that the 40 that this researcher currently has is clearly insufficient if they want to have 95% confidence with this very, very restricted margin of error. A possible interpretation of what we've just discovered here, and something that's worth pointing out here, is that the researcher already had 40. So the key observation here is that the researcher needs 67 more employees in the study. But the important takeaway here is that they could have more. So the important observation is probably more accurately written as noting that 67 is the minimum. If they had more, then they would definitely hit the 95% confidence with an error of 1.5, no problem. So that'll conclude our conversation today about section 6.1 with our introduction into confidence intervals under the assumption that the standard deviation sigma is known. That's the most important part here for section 6.1. Next section, section 6.2, we're going to revisit the notion of confidence intervals, but now we're going to ask what happens and what the procedures are if you don't know the standard deviation. It's a little bit different, and we'll see a little bit more of that in the near future. Until then, thanks for listening, and good luck with everybody's homework as you practice and all of the techniques that we've talked about today, and I'll catch you all in the next one.